Despite the efforts of many brilliant people, general relativity and quantum theory still appear to be incompatible. This suggests that a more fundamental theory is required that admits both of these as very good approximations in their own domains of validity. A further major issue that occurs in cosmology is the requirement for dark matter in order to explain the rotation of galaxies and the formation of galaxies themselves. This video describes how an abstract theory that I discussed in a previous video tackles these problems. The essence of the theory is that physical universe is an interpretation of the mathematical universe of integers, with the continuum merely being a very good approximation at low resolutions. The basic objects from which the universe is constructed are abstract entities that have no intrinsic material properties, and the only intrinsic property that they do have is an identity, but these identities are exchanged to satisfy a zero information content for the abstract universe. Material properties are then defined as relationships between the abstract entities. The theory of exchange of identities is essentially the theory of the symmetric group, and this leads to a form of quantum theory. Thus, the relativity of matter is actually the origin of a quantum theory. And the question is, what relationship does this relativity have to special and general relativity? This question is answered by examining the nature of space and time that arise in the abstract theory. The abstract universe consists of all possible numbers of entities, and the ordering of this number provides an evolutionary time, which you call it n, the number of identities. For each value of n, a spatial section is provided by taking sets of k entities at a time, with the value of 3 for k being the most relevant to comparisons with physics. The values of the identities can be used as primitive coordinates of a k-dimensional space, but with the limitation that these coordinates can only be said to lie in the range 1 to n, rather than having a specific value owing to their exchange. This means that the set of k entities with their coordinates define the basis for a Stiefel manifold, and associated with that is an affine manifold of Grassmann spaces, GNK, of k-dimensional subspaces of an n-dimensional space. The universe as a whole then consists of an ordered sequence of these Grassmann spaces as n ranges from 1 to infinity, i.e. there is a precise start but no end to this universe. In addition, these coordinates satisfy a Heisenberg-type uncertainty relationship with a formal momentum defined as an eigenvalue of a cycle of length n of the symmetric group. The first comparison to make then is with special relativity. The biggest difference is that the evolutionary type n causes an increase in the quantity of matter in the universe. In order to exclude this effect for comparison with relativity, we have to consider the situation where the abstract universe appears simply to consist of multiple copies of the Grassmann space GRNK for a specific value of n, let's call it t. Now this space then is k times t minus k, i.e. 3t minus 3 dimensional, and together with the evolutionary time, that adds an extra dimension. This Grassmann space cannot be described in terms of a single coordinate neighbourhood, unlike Minkowski space. In fact, there has to be a minimum of one coordinate neighbourhood for each choice of the k, i.e. 3 entities that make up the discrete subsets, and hence the three-dimensional space. So physics would then correspond to the choice of simply using one of these coordinate neighbourhoods alone to describe the whole space. Obviously, for a pure continuous space, that is not valid, but because the underlying space is actually discrete, then any discrete space can be embedded in any higher dimensional continuous space, so that the physical approach should still be valid as a good approximation in this type of abstract universe. Subject to this limitation, then special relativity arises from transformations of the coordinates and their directions and a subjective time. This subjective time is measured along the real time of an object in the space, hence it sort of differs in general from the evolutionary time. Early in the history of relativity, it was shown that special relativity could be obtained from projective geometry of space. The space involved is a hyperbolic space of signature 1, 3, with the 1 referring to the non-compact dimension, i.e. time, and 3 to the spatial direction. And this velocities are inhomogeneous coordinates of the projective space. Projection occurs from a finite point in space rather than from the point at infinity. This makes no difference to what you would expect for the velocity of light. Projection from a point of infinity will correspond to an infinite velocity of light, whereas the finite point leads to a finite velocity of light, and indeed the maximum velocity which can occur in this particular interpretation I'm describing is equal to n, the ratio of the largest distance to the smallest interval of time. The Lorentz transformations which arise in this hyperbolic universe then lead to the relativistic relationships between space and the subjective time coordinate. The exchange operators from the symmetric group all occur at an instant of the evolutionary time. Hence, these provide correlations between distant parts of the universe which would not be expected in the ways on the basis of the normal causality of relativity theory. So this provides a possible explanation of quantum entanglement. In order to discuss the relationship with general relativity, we need to examine the nature of this space-time in greater detail. It's also worth pointing out that the nature of the universe is epicyclic. Early in the days prior to Newton, epicycles provided quite a good prediction of the motion of planets, though the central gravitational field was much more successful in providing a neat theory. However, on the grand cosmic scale of the universe, it's clear that the motion of matter in general is epicyclic in its nature, i.e. planets revolve around stars, stars around centres of galaxies, galaxies around centre of gravity of clusters of galaxies, etc., etc. So this type of motion should in principle be amenable to some form of harmonic analysis. And in the case of discrete matter, then all these cycles can be described through the mathematics of the symmetric group. It's well known in the basic theory of the symmetric group that cycles can be classified in terms of their lengths and the numbers of these cycles. So this is exactly analogous to the way that the Young tableau of the representations are defined in terms of partitions of the number n, or for the specific case of comparison relativity, the number t, the absolute cosmic time which we're treating as constant. So any set of cycles, all the operations of the symmetric group are classified in terms of the lengths of these cycles, and they're labelled as the length of the cycle and the number of cycles at that length, so that the sum of the products of length and the number of cycles of that length add up to the value n, or t in this particular case. The extreme cases of this are a single cycle of length n, or t in this case, or the exact opposite, where we have n cycles of length 1, i.e. trivial cycles. All of this is actually important because the theory of the cycles forms the basis of the homology and cohomology of a Grassmann space. Now this Grassmannian sort of structure provides an explanation, or a possible explanation, for the skeletal structure which is required for the formation of galaxies in the usual Big Bang theories, whereby the dark matter provides a skeleton. So hence there is a possible explanation arising from this. The homology and cohomology of Grassmann spaces is very well known. It is based on dividing the space into so-called Schubert cells to form a cell complex. These Schubert cells can be indexed by a k by n minus k dimensional partition. These partitions are in bijective relationship to the sets of k vectors that define a single point. The Schubert functions that characterize these partitions obey the same multiplication rules, i.e. the Littlewood-Richardson rules, that are obeyed by the Schur functions of the symmetric group, thereby providing a relationship to the underlying theory of the symmetric group. The relationship between mass and curvature in the theory of the abstract universe depends on the homomorphism between polynomial representations of the general linear group and the Schubert calculus that occurs in the Chern-Weil theory of characteristic classes. In the physical case of the abstract theory, the three formal momentum vectors define eigenvalues of the energy momentum tensor, and each entity also behaves like a string in its own two-dimensional space-time. A fourth component has to be added dual to the evolutionary time, so this bit is not dependent on the symmetric group itself. Having got these four components, then choice of these values defines a cross-section of a complex bundle with structure group GL2C modulo SL2C if a complex structure is defined equivalent to the light cone structure in physics. There is then an isomorphism between the Chern classes and the symmetric functions. The relationship of the abstract theory to conventional physics can be summarized in the following points. Firstly, the relativity of matter gives rise to a quantum theory. This quantum theory is similar to quantum theory of physics inasmuch as the position and momentum obey Heisenberg-type uncertainty principles, but differ through the commutation relations of gauge fields carried by the exchange operators, are the commutation relationships of the symmetric group. In addition, the commutation relations for the discrete particles result from the projective anti-commutation relations of the symmetric group. When it comes to space, then the space of this abstract theory, regarded as a continuum, is a sequence of Grassmann spaces of increasing dimension. Grassmann spaces cannot be covered by a single coordinate neighbourhood. To get a comparison with the Minkowski case of physics, this would arise in the case of a single coordinate neighbourhood only, and also subject to the restriction that the evolutionary effects are neglected, i.e. a constant value of n or t in this particular theory. The Grassmann space also has a large-scale structure related to its homology, and this is potentially an explanation for the web associated normally with dark matter in contemporary physics, which is required to explain the formation of galaxies. The simplest modification of general relativity that could be made to make it compatible with the evolutionary effects in the abstract universe are to add a creation tensor C mu nu to allow for the creation of new matter. An additional feature is that the symmetric group acts in a way that introduces long-distance correlations between features of the universe that would not be expected in normal relativistic physics, and this may provide an explanation for quantum entanglement. So I hope these ideas help to provide some explanation of the relationship between quantum theory and general relativity.